It looks like it's fixed now.
Okay, I've just realised I forgot my bio. Yeah, I've got a live logo, so 2 seconds and then we'll kick off. Okay, so hopefully my slides are on display and we're ready to kick off, and that I can be heard on all channels. So yeah, welcome to this session. I'll kick off with saying this particular session is very fast-paced and quite dense, but we will have a 5-minute break in the middle, both for people just to chill for a moment and to allow people to ask questions if they are interested. Questions are very much welcome via text message. We're running this in a webinar format, so you're all muted by default. If anybody really wants to ask questions in speech, you can ask for that in the text and Christine can unmute you. That's only if you're connected via Zoom, however. There's a link to the slides up here. Christine will add that to the chat for anybody who wants to follow the slides as we go. And I'm kicking off with a very short biography, not really because I want to wave and tell you all about me, but more so you can examine my prejudices. You know, where I come from influences how I think about debugging, and that's important to be aware. So, you know, I started my career at ST, where I was a real-time operating system engineer at the time when operating systems were part of the toolset. So you got your C compiler, you got your linker, and you got your real-time operating system. And as the set-top box industry, which is the part of ST I was working in, pivoted from custom RTOSes to GNU Linux, that's where I followed. And during the subsequent years, I worked across the entire stack of a set-top box, from networking through to being the kind of audio specialist for a couple of years, and moving right down from, you know, writing code in C libraries up to high-level software architecture. I did end up working through quite a lot of the software. In my final years, I came in as the tech lead for a project to rewrite the whole driver stack from scratch. And that project was running behind, and I was brought in to have strong opinions to try and help people move more quickly. During that time, that's when my role really became consultative for the first time. My job wasn't really to code the new driver stack, it was to support and help team members who did. And that's where I became interested in kind of training and talking to people about these things. I then came to Linaro, and after a little bit of time in the Kernel working group, became the tech lead for the support and solutions team at Linaro. So the nature of being in a multifunction support and contract engineering team is that my work is very varied, but essentially it's all still centered around that background in tools and operating systems, that I am interested in tools, I like tools, and I'm here today to tell you all about tools. So this particular course today, we're going to be talking about a lot of different debug tools, just to try and break the idea that debugging means firing up a debugger. It's not that firing up the debugger is ever a bad idea. You know, I maintain KGDB in the Linux kernel. I care a lot about it, but we won't be talking much about it today because we want to be looking at other ways to debug and study and find problems. So what I will say is we're going to cover a lot of these tools, and every single one of those tools could occupy at least an hour in a conference schedule. And within the scope of 2 hours, I'm going to describe all of them. So we're going to have to cheat a little bit. And the cheat that we're making is we're not showing how to use the tools. We're describing what problems they are good at solving for us. We're going to look at how the tools work internally so that you can see a little bit about how they can be used to solve the problems you might find in day-to-day debugging. And even more than that, we're going to study each of these tools through a lens, a story about what type of debugging we might be doing when we break out these tools. Before, however, we move into all those stories, there's some kind of basics that I want to present to people. We've called it the basics slightly tongue-in-cheek, because by the time we talk about the very advanced failing early tools, basic is not the way you would describe these tools. But essentially some of the sort of fundamental ideas and concepts behind debugging. So there's a number of ways you can divide debugging, but I want to present you some ideas based on the idea that there's these three big pillars in the debugging world. There is tracing, which is the gathering of events into some kind of event log during system execution. Events would typically have some kind of timestamp associated with them to assist their interpretation. And for anybody who's wondering, printk, when you get right into what printk is it is a moderately low performance form of tracing. So printk is a fundamental debug tool. I will not tell you anything else in this session. Printk remains a very valuable form of debug tool. Profiling is the other, another of the pillars, which is slightly different to the gathering of events, because instead of gathering events, we're gathering statistics during system execution. So what those statistics could be are the threads that are dominating the CPU at a high software level, down to which branches of your code are most likely to miss the L2 cache, depending what you're trying to profile and what performance characteristics you're trying to study. Profiling is quite often determined from an event stream, so you can use trace and profiling. They have this interrelationship because they're quite often hooked up to the same events. And some of the Linux profilers even actually work by filtering an event stream after the fact. So tracing is studying events event by event. Profiling is crunching statistics to tell us, to gather statistics about how the system's been operating. And then finally, we have stop the world or post-mortem systems. So a classic debugger, GDB, is what I would call a stop the world debugger. So the concept of it is it stops all execution on the target. You can then interactively manipulate with the target, and then you can start the world again and it will continue running, if you are very lucky and you haven't got too many real-time deadlines. And that's where post-mortem comes in that post-mortem is simply a special case of stop the world, where we have no expectation whatsoever of ever restarting the world. So you can even view an oops trace as a kind of automated stop the world analysis. It stops the thread, it dumps the registers, then it kills the thread. So post-mortem and stop the world are very closely related, and a lot of post-mortem debuggers actually use a traditional debugger to study the core dump that you've gathered in a post-mortem. And then finally, I've talked about these towers, but they are they're interrelated, and combinations are very powerful. Without question, my favorite combination is that of a trace log coupled with some kind of mechanism to stop the world when something's gone wrong, so that we can combine the memory state of the system with the trace log to help us walk a little bit backwards. I noticed the comment in the chat about links to the slides. You have to keep reposting the link to the slides because people who join late don't get to see the previous chat in Zoom. Okay, so failing early. Failing early is a fundamental concept for me, and it's built into the various bits of Linux debugging tools. So failing early basically means trying to cause us to enter the debugger, enter some kind of post-mortem system as early as possible after the fault has been observed. And there's a variety of obvious reasons for that. System tracing tools quite often use circular buffers. printk certainly does, and various of the tracing tools can also be tracing to circular buffers. And that means that if you don't fail early, the evidence of what's gone wrong may simply have been evicted from the buffers long before you ever bring the system to a halt. Also, bugs can injure the system. So the earlier you can fail, the less significant the damage is likely to be, and the more likely are you able to study and find out the correct symptoms. Talking of which, the symptom you've actually studied might be a second order effect. If you're saying we've got some memory corruption, the next step is how did that memory corruption happen? Was it to do with two things not having correct locking, or was it something else? So the actual problem you initially observe could easily be a second order effect, but the earlier you can fail after the first order effect, the more likely you are to be able to figure out what it was. And then finally, trace data, if you're using big trace, is very, very large. And if you can fail early, or at least log a message when something bad has happened, then you can navigate the trace. When you do big traces, particularly hardware trace, then actually finding the the opcodes that you care about among this dense forest of millions of opcodes is incredibly difficult. So having some mechanism to recognize a fault is a great way to help you navigate those huge trace volumes. So moving this away from sort of philosophy and into the real world, most of the Linux debugging tools we're going to talk today, or not most of, but many of the Linux debugging tools that you find in the kernel hacking menu are there to automate failing early. We'll look at some of those in a minute, but most of those tools report failures via printk. And it has to be stated that printk is very defensively coded. There is probably not a more defensively coded piece of the kernel. And that's in order that the message should come out. There are ways to break printk, of course there are, but it is quite difficult to do it. You have done well if you've managed to break your system enough to break printk. It's something to write a blog post about because it's not common. And just to make the point, git grep does make it quite easy for you to map printk messages and match them to the corresponding source code. So if you see odd messages, you should always be able to look at the line of source that issues them. Moreover, if you can't fail early using the automated tools, then think about whether you can recognize the symptoms of your bug using a piece of code. So once you've done first stage sort of triage of the problem you're studying, if it's not obvious from that triage what's going wrong, then try to find ways to automatically recognize the bug so that you can sprinkle that kind of recognizer all over the kernel. And that gives you a couple of useful properties. It means that you're now going to fail earlier, closer to the first order symptoms that you're hoping to identify. It also allows you to reason about how recently the system was damaged, because if it didn't fail when the recognizer previously ran, then you know that within this particular time window was when the damage occurred. And that allows you to then start looking at things like the trace that will tell us which threads have been on the kernel, so we can find out what's been running in that gap between damage being created and damage being observed. So again, now we're going to try and get concrete, because I don't just want to spend the whole 2 hours talking about philosophy to everybody. So there are common techniques in the kernel for a number of different fail early mechanisms. And actually, the first one I've put up here is not a true fail early technique. It's actually a simple form of static analysis, but it's still worth talking about. So Stack Overflow detection in the kernel is quite difficult, or historically it used to be difficult. And so the stacks are also very small. 4K or 8K stacks are not uncommon within the kernel. So frame warn is simply a mechanism to tell you if you've got large stack frames. If you've got that function that allocates a k-long array in the middle of your stack, it has a very strong chance of overflowing. So a static check to make sure that you didn't accidentally put an array on your stack is there. I mean, frame warn is run quite frequently on kernel code, but it's quite reasonable to run this in advance and check if you've got a lot of separate vendor code that your code is also in good condition with regard to stack usage. Then we move on to the true fail early tools. So there are two main sort of Stack Overflow things. This one's always hard to say as well. Shared stack end check is a mechanism to check when a task is shared schedules to find out if the stack has previously overrun. It's quite an important check, particularly on ARM32 for reasons we'll see in a minute. But essentially, when you try and deschedule, it will look for a canary word at the end of the stack, and if it has been written over, then it will conclude that the stack has been overrun and warn you that during this particular time when this thread was executing, the stack overflowed. If you are running on a 64-bit system, you can also use VMAP stack. So VMAP stack does require quite a big address space, so you can't run this, I don't think, on a 32-bit kernel. But this one works by effectively allocating the stack from virtual memory instead of from the big kernel pages. That allows the stack to have a guard page, an unmapped page between it and any of the next piece of memory. So to have an 8K stack, you allocate an extra chunk above it, which in the address space, which doesn't have any memory associated with it. So if you read or write from it, then the system will immediately take a fault. That means now we don't have to wait for the task to deschedule. The very moment you step outside the stack and try and save or restore a value to it, then you will trigger a fault and you'll see exactly that you've overflowed. So VMAP stack is very strong and very able to prevent you from getting run-on problems. It has a tiny performance penalty because by using virtual mappings, we end up using small traditional pages to map instead of the huge pages that are used to map the kernel, the main kernel. But it is the sort of thing that can actually be turned on all the time, and I would imagine on things like Chrome OS it probably is. Moving on from Stack Overflows, we've got the memory debug techniques. So there's a couple of ones, there's more than this in the kernel if you go and study the kernel debug menu, but these are the ones I'll bring to people's attention. The first one is slub debug, which is debug code added to the slub allocator to look for things like double freeze. It can do poisoning, which is where you overwrite when you free, so that you can't do use after free without hitting these strange pointer values. It can trace the logs to help you find leaks. So trace the allocations and deallocations to help you find leaks. I've printed this one as a kernel command line argument rather than a config option. And the reason for that is that slub debug was present originally in the code base and turned on all the time. Sometime after slub was introduced, then slub debug was added the config option. And that was mostly to try and squish down onto teeny kind of microcontroller size systems and maybe some of the sort of 4 megabyte DDR2 style old systems. So slub debug was added primarily to use code size and isn't really performance controlling. There's not really much penalty from turning it on. Almost every distro I'm aware of leaves this on by default. It's not something you should turn off recklessly. It's because then it's there for you to use on your production systems if you need to. There are, however, some other things that do have some costs associated with them. So debug page alloc is like VMap stack, able to use the MMU to detect access to free pages. It's basically a kind of recycling list. So when a page is freed, it becomes unmapped, so you're not able to see it anymore, and the pointer becomes invalid, and you use after free, and you'll get an exception. Again, there's not enough address space on an ARM32 system to do that. But you do also have page poisoning, which is similarly when you free a page, it gets filled with the poison pattern, and that gets checked when you reallocate, so that when you free, reads will give you strange values. Poisoning usually uses a recognizable hex value, CCC, that style of thing. I can't remember the actual numbers for each of these things, but you can look them up. And the pattern is validated when you realloc. Moving on, we've got lock debugging. So debug mutex is up here, but I would like to warn you, it doesn't do quite as much as you think. It's basically adding sanity tests to make sure you've not broken the kind of mutex contract. You know, mutexes have some properties. They are not semaphores, they are mutexes. They must be freed by the thread that locked them. So unlocked by the thread that locked them. They must be limited to certain calling context, etc., etc. So it's not any kind of deadlock detection. It is simply checking that you have not abused the API. Debug atomic sleep is basically a mechanism to yell if we try to sleep from atomic sections. So if we try to deschedule, we're not allowed to deschedule, we'll get told about it. That's a very important and useful bit of failing early. Debug lock alloc is essentially memory debugging for locks, because using locks after free really does cause some quite exciting problems. And I'll also mention the lockup detector. So the lockup detector on all the current ARM systems is using a HR timer IRQ as a watchdog to make sure the scheduler is functioning correctly. On systems like x86, the lockup detector also enables a periodic NMI to make sure that the HR timer interrupt is running correctly. So it's a two-stage thing. The HR timer IRQ watches the scheduler, and the NMI, non-maskable interrupt, watches the HR timer. At the moment, ARM64 systems do now have sudo NMI implemented and upstreamed, and there was a patch set from Julian Cherry to bring the full NMI support to the PMU, and as it happens, the lockup detector uses the PMU to generate NMIs. So that patch set came out, I think it was released middle of last year. It's not been picked up. I've got a member of my team chasing that up at the moment to see if we can push it forward a bit. And then finally, this section, RCU stall detection, is not a fail early technique, really. RCU stall detection is basically a message that comes out when the update portion of read copy update cannot be undertaken because some of the CPUs are not entering the rendezvous point needed to do that. it's really useful if a CPU locks up, because RCU store detection files. If a CPU stops functioning, hard lockup detector isn't there because we haven't got an NMI. But if one of the other CPUs is running, it will usually end up printing out this RCU stall detection message. What you should take from that from a debugging point of view is if you see an RCU stall detection that won't go away, quite possibly you've got a CPU locked up in a position where it can't take interrupts. It's not guaranteed, but it's usually a fairly strong indication. So with all these techniques, we have to think about the level of intrusion. So runtime debug techniques can and sometimes do require significant amounts of CPU or memory. And to some extent it's proportional as well. The intrusive debug tools can be incredibly powerful and are capable of detecting errors quickly. However, the more resources that debug tool needs, the more likely it is that if you've got a bug that's reproducing, that you will prevent it from reproducing. So it is useful to sorry, I've just spotted there's a question from the chat. I'll come up to that in a second. So yes, it is useful to know how much the intrusion there is, because if you know how much intrusion there is, you can start figuring out if the bug goes away, maybe I can't use this technique to try and find the bug anymore. Somebody's been asking, are these options that we pass the system during runtime? So all the stuff in capital letters here are config options. So they've got a config underscore implicit in front of them. So it's config frame one, config vmem stack, and so on. The stuff that is in lowercase, slub debug equals, is a command line option. So you can see the slub. You can look that up in, what is it? There's the command line options dictionary in the kernel documentation directory. So you can look up the arguments you can send to slub debug in there. Okay, so other thing about levels of intrusion is that does mean that some tools cannot even be run on low memory embedded systems. And as embedded system programs, we do have to be aware of that. So in some cases, you can run the tool, but not on the full system. You can run subsystem or maybe unit tests, but you may need more resources to run the full system. This does depend very much on the thing you're running. I've got some examples below of some of the useful but expensive debug tools. So poisoning is a peculiar thing. Poisoning overall is not usually that costly, but if you have a specific workload that provokes a lot of memory allocation, then poisoning becomes very expensive, because it's basically a continual mem copy every time you allocate and deallocate, or mem set actually every time you allocate and deallocate. So poisoning is not usually too bad, but there will be specific workloads where it has some big impact on performance. Prove locking, that we'll talk about in a minute, makes the time taken to take locks a little bit unpredictable, but it does actually settle down and become quite quick after a while. And then we hit some of the really big guns, things like the kernel address space sanitizer, which is a mechanism to instrument every memory access in the kernel and perform a validity check at runtime to make sure that that pointer is valid. So you can think about how powerful that is. We can now know that when we read from memory, that A, it is initialized, we're not reading uninitialized memory, and that it is valid that we should read it, that it's not a piece of kernel memory that is not currently allocated. However, to maintain the state for the kernel address space sanitizer, we end up using 1/8 of the available memory to record which bytes are valid, 1 bit per byte. The heaps become less RAM efficient because they have to have guard stuff between them. We have to have recycling lists to avoid reallocating memory straight away, and so on. And the cost of the instrumentation is that the kernel is running about 3 times slower than normal. Won't affect the user space. So again, it does depend on your system profile. If most of the computation is done in user space, running the kernel address space sanitizer doesn't cost that much if you've got the RAM to support it. But there will certainly be kernel code paths that are quite slow. So just to wrap up this failing early section, and why I said basics was a little bit tongue-in-cheek, was a quick summary to show you some of the most advanced tools and what they're actually doing for you. Why that despite the cost, they are definitely worth running. So the first one we'll look at is prove locking. So on the left, I've talked about two threads. Now, don't think of these as user level threads. They are threads of execution. One of them is probably an interrupt handler, to be honest, because this pattern where you've got log subsystem, lock driver, and in another execution context, you've got lock driver, lock subsystem. It's usually an interrupt handler where you lock the driver first and then take the subsystem. So this particular thread is a risk of red deadlock. If that thread schedule ever happens, and the other thing is, don't assume this is linear C. Obviously, nobody writes two locks to the driver and subsystem side by side. They are locking with no other events shown. So you've probably got a collection of function pointers and other function calls through function pointers between the two takings of the locks. It should not be immediately apparent from reviewing the code that these things are a potential deadlock. So anyway, on the left, we've got two execution contexts, one that have locked the locks in either reversed order, and at the point you attempt to lock one of these, there will be a deadlock because the other one is already taken. If they've both started by locking the one the other one wants, then both of them will then try to take the second lock and will not be able to get it. Now that window is usually quite small. This is the sort of thing that will often not be discovered by developers while they're developing. It's the sort of thing that has either final QA or the OEM puts on a line stop and you have to fly around the world to fix it, or it's discovered in the field. It is a difficult problem. It will happen rarely. It will not be found at a convenient time. On the right-hand side, we have a single execution, think of them as SMP CPUs for now. So we have a single CPU that's run a collection of lock and unlock sequences. So it has locked the subsystem, it has locked the driver, and it has remembered that particular call stack and the lock sequence that got to it. You then unlock the driver, unlock the subsystem, and then we do the lock in the opposite order. We lock the driver and then we lock the subsystem, and it remembers that lock sequence as well. And at that point, it goes and compares the lock sequences that is observed. It is somewhat optimized because these aren't actually single locks, they're actually lock classes that are being studied here to shrink the problem down, because there are quite a lot of locks in the kernel. The algorithm to check that whether or not they are running in the same order is a order n squared algorithm. It's one of the reasons it causes performance trouble. So there are lots of optimizations to avoid these checks when at all possible. So it looks at the lock stack, hashes it, uses that to avoid comparing the lock sequences when it can. But ultimately what will happen is when you have got the second lock sequence that is risky observed, it will dump the call stacks for every lock that has been involved in this, telling you where it was allocated from, so that you can then go and try and work out which of those call stacks is the one where you shouldn't have taken the lock in that order, or where you should have released the lock before you went back to the subsystem, for example. What that means is you now no longer have to hit that tiny timing window to find our problem. We have failed early, and in actual fact, we have meant that the bug never happened, and we've got a way to fix the bug before it's ever been reproduced. It's very, very powerful. The other one I want to talk to you about is kernel hardware address space sanitizer. This is a specific ARM64 CPU feature because it relies on a feature of the MMU. This was implemented by Google about a year and a half ago, I think. Actually more than that. But it was a Google work that was upstreamed. I can't remember quite when. And it works by ignoring the top byte of pointers. That's the underlying MMU feature. So when the MMU looks up a pointer, it is capable of ignoring the top byte. What that means is that software can store any interesting value in the top byte and the MMU will ignore it. So what kernel address space sanitizer does is every time we allocate a buffer, we give the pointer a tag and we store in information about the memory what tag that memory is supposed to have. And then we instrument every memory access to compare the tag and the sort of tag that's in the shadow memory. If they match, it's great. If they don't match, we report an error. Now this has some great properties. So it does actually use less shadow memory than the kernel address space sanitizer, but that's partly because it is less precise. Because it's storing an 8-bit tag, it gave up on having a tag per byte because that would have been a 1-to-1 mapping. It now tags every, I think it's 32 bits. So that's why it doesn't require as much memory. It must be 64 bits actually to get the ratios right. It tags chunks and therefore it's not quite as precise. Which is why it won't catch some small out of bounds accesses. If you go the last byte, or if your the last byte of an object that's not well aligned, it won't detect that you've gone to the wrong thing. But you also get some power that you do not have in the normal case. So if memory is recycled and reallocated and becomes valid again, it will have a different tag to the tag it had previously. So if you use after free memory that's been reallocated, we will still detect that we've tried to use a stale pointer because we've reallocated memory, but the tags no longer match. So it's a really neat feature. It does cost a lot of performance, and that's roughly what we want to speak about those tongue-in-cheek basics. Partly, A, that failing early is important, and B, showing you the length to which some of the kernel developers have gone to implement fail early for us. So are there any questions pending at this point, Christine? I don't think so. Okay.
Nope, none right now.
Excellent. So feel free to verbalize them as we go if I'm missing the fact they're written down, because you'll see me turn down here. This is where my chat screen is, but it's a tiny font and I'm trying to pay attention to what I'm telling people. So,
Okay,
feel free to interrupt and verbalize if it feels right.
Sure.
Okay, so we're now going to move into the stories and actually look at some of the tools beyond the failing early mechanisms. So the first story is actually the one that happens quite late in the development process, but I'll explain why we've picked this one first in a moment. But we've called it I can't reproduce, but my customer can. Essentially, it was running great when I was developing it, but I gave it to my customer and they keep reporting a problem with it. Maybe I don't even have the equipment that they say they're using to report it. You know, I've already done 3 on-site visits this year. I don't want to travel again. I'd rather stay at home and work on it there. This is a particularly relevant story in the current world situation, but to be honest, I don't like getting on a plane to fix bugs, even when there's not an international crisis going on. So in each of these stories, we've got kind of some scope and some notes just to help us understand the story. So odd behavior could mean any of the behaviors we're going to discuss today and more. We don't really care what the odd behavior is. We've deliberately left these stories a little bit loose so that we can illustrate different tools and things like that. Whenever you've got a remote reproduction use case, the level of skill that the customer has may well be different from ours. Obviously, some kernel programs believe that their level of skill is always sky high and everybody else is rubbish, but that's not quite what I mean. Essentially, that if you propose experiments to them, you have to verify with your customer that they are capable of following those instructions, that they understand them. And the problem you have the opposite way around, if they know more than you do, they get very unhappy about running your experiments and try to run something completely different. So yeah, it is worth being aware that the level of skill of the customer may be different to ours. And we're going to assume that the customer is probably external to your organization, because if you're working with an internal customer, maybe it's a time zone, but you know, perhaps you should have just started up a phone call, telepresence, VNC, you know, pair programming via remote technology to launch a joint investigation without actually, you know, sharing log messages. So I'm going to take this question because it's going back to here. So so somebody has asked about the use after free concept in hardware address space sanitizer. I can't spend too long on this because we will run out of time, but essentially when you've got this tag in the top pointer bits, and in shadow memory, you've kept a tag of what the pointers are supposed to have in those top bits. The idea is that you've got a chunk of memory and it says, if you access address offset plus 4K, then the tag should be 17. If you have a pointer that is stale, that's been previously allocated, there is only a 1 in 256 probability, well, 255 actually, 1 in 255 probability that the tag will be 17 by chance. That means that in, you know, more than 200 out of 1 cases, you will detect that use after free because the tag on the stale pointer will not be 17 as it says it should be in the shadow memory. Essentially, whenever you reallocate a memory buffer, the shadow memory is marked up with a tag that it did not previously have. So that's what allows us to detect use after free trivially rather than simply validity of pointer. Sorry for that aside. We're going to move on with this story again now. So there's some consequences as well as from that scope. We can assume whenever you're doing something remote, debug cycles are going to take longer than usual. That roughly means you have to think more carefully before you propose experiments because they have a bigger cost to implement. If you've got a customer whose skill is less than yours, then the deployment of the debug tools has to be at the customer's level, not your level. So they have to be simple and easy to deploy. If you tell them to plug in a hardware trace device that they do not have, they will not be able to help you. And ultimately, if you're doing tracing, profiling studies, you have to be able to get that data back to your desk for analysis. So the first and most important tool on any remote investigation is nothing to do with debugging, really. It's a source navigator. Because it is important for you to read and understand enough of the source code that you can kind of study your way around these things. So effective source code navigation is always important, but by using the source navigator to prove and disprove things, we can avoid debug cycles. Simply put, you have this theory that maybe this has happened. If you go and work out how exactly the printfs work, you can prove whether or not it happened in some cases, because you can say, oh, that can't possibly happen when this happens. To learn those kind of interactions between the print messages that they've sent you, and I'm going to assume that you've always been sent a demessage buffer. To learn that mapping, use the source nav. That's how you discover that additional information about what's happening in the stack trace, what's happening between the print messages. I don't have any.
Daniel, to the chat.
Yeah.
From YouTube.
Oh, I see. Okay, so kernel address based on. I'm going to take that one at the end because I was going to keep interrupting this. I'm not going to keep jumping back if we've gone too far ahead. So can we keep a note of that one? I'll pick that one up at the end. So I'm not particularly invested in whether you use Cscope or some other indexing tool. I don't care. However, there are developers even today that have not got indexing tools integrated into their workflow, and to people who have not picked a source nav, this is a sane default. If you do make Cscope, then the kernel will automatically index the source code exclusively for the architecture you're working on, because there is a phenomena if you search for things like spinlock init that you get 20 implementations, one for each architecture. That can be useful if you're trying to write portable code, but it's not useful when you're debugging, because you only really care about the architecture you're working on. So it does know what arch you're building on, and it only indexes the arch directory for the system you're working on. And then in most cases, Cscope you'll find is already integrated into your editor. Vim, Emacs, other editors are available. You can use C tags. You can make C tags. You can make global if you're using GNU Global. So there are multiple indexers implemented in the Linux kernel. You can type make help and find out what they are if you are interested, but it's a same default, it works. The only thing to mention is that there is a quirk with Cscope and a couple of other indexes that if you ask for the definition of struct foo, it shows you every definition of struct foo. Sorry, if you ask for the definition of struct foo, it shows you every declaration of struct foo. In other words, when struct foo star something appears in a header file in a function prototype, that is declaring struct foo implicitly inside the function prototype. It may be defined somewhere else, but it is implicitly declared, and Cscope will take you to every single one of those things. In other words, you can get 200 implements of struct file and not the definition. So if you're having a problem where you can't find the definition of structure, use the source code formatting standard to search for struct, name of struct, curly brace with git grep. And that's just a workaround for those cases where you can't manage to look up the thing in a better way. Second part of source nav is mapping print case to the source. Like I say, regular expressions via git grep are exactly the way to do that. Key things are that obviously you don't grep for the timestamp, that should be obvious. Equally, you do not grep for this label either. So the label that appears before a printf message is not usually found in the string in the source code for two reasons. If it is a dev message, so you're using dev error, dev info, things like that, then that tag is the name of the device, it's dynamic. And if you're using PR info and things like that that do not have a device pointer, that tag is actually hash defined much further up the file and gets automatically included in every message. So in neither case is that going to be part of the string, so you exclude that from the thing you're grepping for, and obviously then you wildcard arguments. So if you see this XYZ found 10 widgets, you would tend to craft a regex that looks a bit like that, and that should guide you towards the message in the source. There's a certain knack to creating regex. You get a sense after a while of which words are likely to have been included. occasionally get caught out. If you try grepping for boot console, you won't find it, for example, because that's done as a %s console and the boot is somewhere else. But you know, in general, you can start getting that sense of mapping of regex to source code. So printk, I'm not going to suggest that printk at any point is not a terrifically good debug tool. It is. It is easy to use. Everybody understands it. It is robust, as I mentioned at the start, and it is almost always there. Nobody sane ever compiles out printk. I have worked with people who've compiled out printk to optimize the boot times, but in general, very few people turn off printk because it makes it too hard to work with the machine if you do. So that means you can always get the D message back from your customer, and you should. That means you can study the existing log buffer and form a collection of theories about possible failure. Standard working practice then is you modify the code to enrich the log buffers in ways that could prove or disprove each theory that you've got about how it might have failed. You share with the customer and you cycle around again and again until you hit the messages that prove what's gone wrong. It's a slightly slow approach, but if you are diligent with the source nav and you produce multiple theories, you're not lazy about it, you spend an hour, 2 hours with the log message and the source buffer, and you have 10 theories, so that you've enriched it with 30 new log messages, and you share it with the customer, you zone in very quickly. A very important thing to know about printk is that at the moment, if you have an embedded system with a UART-based console handler, then messages that go to the console, performance is extremely poor. And the reason for that is that I mentioned printk is robust. One of the things that happens to make it robust is that the CPU spins while the UART is sending out the message. And at the normal baud rate that we run these things, that means 80 characters is about 3 milliseconds. So if you print half a line of text, the CPU will sit there wasting time for 3 milliseconds. That means that heavy printk that goes to the console is tremendously intrusive. You can easily, just with a couple of printf messages in the wrong place, start missing all your real-time deadlines on a system. This is only when it goes to the console. It is not printk that is expensive. It is issuing to the serial port. So if you turn the console to quiet and access the log message by a D message instead, if the system is survived at the end of the process, then you will still get good performance. If you are able to crash and attach the debugger and extract the D message buffer post-boot, post-crash, again, you don't have to have it actually go out to the console. So disabling the console or not printing at the console level is a really effective way to get printk to run more quickly. Finally, while we're talking about printk and dmessage, it's worth understanding things like PR debug and how it works, as well as dev debug and other related macros. So both PR debug and dev debug are disabled by default. They do not compile in. Even when you enable them by some mechanism, they will output at level 8, which means they don't go to the console by default. Assuming you haven't messed with the default config level or console level in your kconfig file. So they're disabled by default, they don't even get compiled in, and even if you compile them, they won't go to the console. They will at that point go to the dmessage buffer. So there's a couple of ways you can work with debug messages. You can, on a compilation unit by compilation unit basis, hash define debug above the hash includes, and that will cause PR debug to become a static print. It's kind of rubbish though, because if you do that, you don't get tags on function names and things like that. So it's a common review comment on the kernel mailing list. You get a dev debug but you fill this with function names, you get that automatically. You do when you're using dynamic debug. So when using dynamic debug, you get nice rich log messages. You can control them very fine-grained, so you can turn on and off individual messages as you go. So in actual fact, when you run dynamic debug, the code is now compiled, but it is not executed by default until you go in and dynamically enable particular debug messages. That also allows you to do things like scatter printks everywhere, even have them go to the console, and then turn on or off different ones and run multiple experiments with the same binary. I hate to say it, but my experience is that the fewer times you can change the binaries, the better, because it's one of the things customers find hard enough to do is load the right damn kernel when they haven't compiled it themselves. I don't know why, but my experience is that the less you can cause people to change the kernel, the better. Am I doing for time? Yeah, okay. I'm not going to go into this one in great detail, but one thing about working with oops traces and print messages and anything else where you've got real pointers, and do keep in mind that some of the kernels are now hashing pointers for security reasons when they print them. But when you are, so if you see kind of pointers that are full of what looks like random noise, that basically means they've hashed the pointer. So recent Chromos kernels, for example, would be doing that. I would imagine modern Android kernels will start doing that soon. But when you can see pointers, when you can turn off that feature for debug purposes, etc., then knowing how to recognize some of the basic information about a pointer, you don't have to recognize that much. The things that are worth knowing is how to discover what a user pointer is. That's actually very easy. A user pointer starts with 16 zeros on an ARM64 system. And kernel pointers start with multiple Fs. The exact split point will depend on which extensions you've got available and a few other bits and bobs. You should then have a clear idea of where the direct mapped kernel pages are. These big kernel pages that I've mentioned before, where most of kernel memory gets mapped. It's also worth knowing what virtual pointers look like. So when you allocate memory from the virtual address space and then attach it to various bits of direct map kernel memory in the backing store, being able to recognize those two differences is very, very helpful when you're looking at logs. So you don't have to know a great deal about the kernel memory map, but being able to classify virtually allocated pointers, direct map pointers, and user pointers is really quite helpful to studying oops traces and saying, the stack looks reasonable, the stack looks sane, this is in the right part of memory. This crash is clearly accessing a virtual address, so that's always quite useful. If you've got a crash accessing a virtual address, that's things like IO remap. IO remap comes from the vmalloc space. So crashes, particularly non-fault crashes, where you've got a synchronous exception, is quite often a bad IO remap. So it's nice to recognize that pointer quickly. But like I say, I'm going to leave that as homework. But just knowing those couple of types of pointers can be really helpful. Likewise, I mentioned a little while back that the stack on an ARM system, it's quite useful to know when it's overflowed. It's not a particularly big issue on an ARM64 system. So on an ARM64 system, you can overflow the stack, it will do corruption, but because of the way the thread info structure is discovered, you don't get problems with the kernel being confused about what thread it's currently running. When you run an ARM system, the thread info is at the bottom of the stack. And when you need to access the thread info structure to manipulate things, we do some maths on the stack pointer. If the stack pointer overflows now, any manipulations you do on the thread info are not happening to the actual thread info, which can lead to a few bits of confusion. Again, these are all things just to be aware of when you've got your messages in your print K buffer, when you've got those kernel pointers printed, when you've got that oops trace maybe that you're looking at. Those are the kind of things you're thinking about. Don't think about stack overflow first, though. It's probably not the biggest problem in the world, but do think about classifying the pointers. Right, so we're now moving on to other ways to get information from the customer back to you. So DebugFS is a virtual file system that has been presented for debug purposes. So if there's any information there that could possibly be useful to you, you should direct your customer to gather it for you. One thing I'd particularly like to bring up is RegMap, because it's a really great example. Any driver that you have that uses RegMap, so RegMap is a register abstraction system that decouples the transport used to read the registers. So by example, in the microcontroller world, in I2C sensors, most I2C sensors are multifunctional. They can use a variety of different synchronous serial protocols like I2C and SPI and a couple of others. It's very, very common for them to support multiple protocols, and they get pin strapped when they're turned on to select the protocol. That means that many of the drivers in the Linux kernel are needing to abstract the transport used to read and write from registers from the actual register reads and writes. So RegMap is what provides that. It does also allow you to abstract memory mapped IO. A number of platforms use RegMap to access registers on the PMIC. So if you have drivers that are using RegMap, then you have a really great feature built into RegMap, which is there is direct access to the state of the registers of that driver in DebugFS. You can simply go in, you can cat a file, and you get a hex dump of the registers of your driver. I kind of hope it's obvious that that's a really powerful debug technique if you want to understand what's going on with your driver and learn things about it while not requiring much sophistication from the customer. From their point of view, they're simply sending you the contents of a file. So DebugFS is a great tool to augment the remote information we've got. Another thing we can think about is function tracing. So if we're not getting anywhere with printk, we could ask our customer to turn on function tracing. Function tracing is the entire topic of next week's session. So if anybody asks a question about ftrace now, I will tell you to wait until next week. I have to concede. But function tracing is a mechanism to allow us to see whenever a function call is made in the kernel. It's quite a simple mechanism when you dive inside it, although there's a lot of machinery needed to make it work. The concepts are very simple. Essentially, all the code of the kernel is compiled with profiling hooks enabled. So PG is a GCC option to build functions with profiling hooks enabled. All the profiling hooks actually do is call a pseudo function called mcount. I say it's a pseudo function because on a lot of architectures, it's not ABI compliant. It has some slightly tweaked function call rules to make it more optimal to call. But then what happens is at link time, the kernel finds all these calls to mcount and replaces them with a no op. And that's the kernel get loaded onto your target. And therefore, it's still quite performant. Because although every function call has this extra NOP in the preamble, NOPs are not expensive things to execute. There is some iCache profile costs, but overall, it's a real challenge to find the cost of turning on ftrace with a profiler. Until you enable or disable dynamically which functions you've attached the tracer to, because inside the kernel is a data structure that allows you to find every function call and re-inject the branch back, this time to a function called ftrace caller that allows us to print the function that's been called. So, like I say, it's very lightweight because it's no ops when it's inactive. It's very, very likely that your workstation has ftrace turned on by default. Most distributions running on laptops will have ftrace turned on because that's how they get problem reports back from the wild if they've got this problem. I will add that I can reproduce, but my customer can't. I can't reproduce, but my customer can. Roughly describes how the vast majority of kernel maintainers interact with the driver authors, because they do not own the drivers that they maintain. So they do not own the hardware for the drivers they maintain. So this kind of remote analysis is very, very popular on kernel maintainers because they can get information back from the wild, study it, and they never have to actually own the hardware on which these things reproduce. Anyway, so it's fairly lightweight. It can be on by default, certainly on kind of engineering builds, things like that. Distributions leave it on. Whether embedded systems should leave it on is a bit more questionable, but it can certainly be on quite late in the development process without costing too much. Once you've enabled kconfig, you get it thing up in DebugFS, and you can do things like echo function to the current tracer, and it will walk through the entire kernel, turning on all the call sites. Some filtering is advisable for different reasons. Partly, we filter to keep the performance up, because if we do it across the whole kernel, then there is a function call happening all the time. So there's a couple of examples here. So we can say this is configuring from the kernel command line. We'll look at how to configure it in other ways next week. But from the kernel command line, you can just say ftrace equals function, and then splatter filter on your driver, so that every time your driver gets called, we get an ftrace event. That's only really helpful for that classic problem where you've got a driver that hasn't actually started up and you want to know if any of its functions has been called. Did it probe? Did it not probe? Did it match? Did it not match? That's how you find out if your function was ever called at all. Saves you having to add the whole print ki started my function, print ki ended my function. You can do all that with ftrace without having to add any of that kind of nonsense logging code to your system. And then you've got ftrace function graph, which is using an additional mechanism to intercept the function returns as well. This particular trace line is not one I'd advise playing with too much because it would absolutely drown you in trace. because it will be tracing pretty much every function call and function exit. It will be enormous volumes of trace. Once you've got the trace, it can be extracted in a number of different ways. So it's accessible from user space, can be gathered with a simple shell script. Trace points, but not function tracing, can be routed to printk. You can arrange to dump it automatically on kernel failures, things like ftrace dump on oops. KDB is quite an interesting way to gather it on some systems, particularly if you are working on a form factor device with some kind of serial port access at the top. If you have something like KDB, then it can crash, it can go into a handler, you can attach a debug tool to the system and use KDB to page through the ftrace buffer after the fact. So KDB is a mechanism to give you essentially, in that case, you're using more or less as a pager. You're not really using its debug facilities very extensively, but it's there as an option. Then finally, you've got trace navigation tools to help you cope at the top level, things like trace printk to put messages in to help you grep, kernel shark to visualize, Lisa to do deep studies. We will look at all of that in more detail next week. The other kind of sets of approaches are classic postmortem. Essentially, can I do a core dump of my kernel? There are a number of techniques to do a core dump of a kernel. So kdump and kexec are probably more enterprisey things because they need quite a lot of memory, but depends how desperate you are. You can run these in the embedded space as well. So the way kdump works is it is essentially a kexec, meaning a kernel bootloaded by Linux itself, that is booted at the point the system panics or has a big failure. And the memory image of the first kernel is preserved across that jump to the second kernel and will be exposed in a file called procvm-core, which can then be loaded up into things like into GDB, studied, postmortemed, examined. The new kernel can exfiltrate that information by any means it likes. It could write it to disk, it could throw it across a network, it could sit there and wait for you to connect to a serial port, and you could spend 4 days copying a kernel in. So it's very, very simple. Essentially, it's a normal kexec with the addition of a -p on it, which causes the dump capture kernel to be loaded into reserve memory, but will only be jumped to when we panic. Like I say, this is difficult to do on an embedded system. So we've got the stuff on the right here. Firstly, kdump images can be loaded by both by GDB and by a special tool called Crash, which is actually a GDB derivative, which has some additional analysis tools to study these dumps. What you can, however, do on the embedded world is develop bespoke tooling to capture core images. This is particularly relevant to audiences of SOC companies because for SOC companies, it's worth the investment because it makes your customers happy. For an OEM, the cost of developing the core dump tool is probably too expensive. So it does depend. We have worked on these at various of my previous employers. And there are a couple of ways you can do this. You can have scripts that run JTAG debuggers and basically copy out the memory image over JTAG. You can also have special bootloaders that recover RAM contents after the fact. Providing if you can arrange to dump the cache at the point of crash, then you can actually reset and recover post reset because the memory doesn't usually fade. The DDR refresh stops when you reset, but providing it's re-established quickly enough, the contents of memory usually stay intact. kdump and kexec have been upstream for quite a long time now, since 4.12, so I would hope most people have access to that if they were interested in it. And that's the end of the first story. I am going to do this story next, and then we will take a short break just to give people a chance to regroup. So this story is my widget has missed its deadline. So this is a much different story to the previous one. This is my widget is supposed to be handled at a particular rate, and as soon as this gets loaded up, I start missing my deadlines, and we've got perhaps dropped frames or something. You'll see my TV background when I talk about dropped frames. My QA team are beating me up. We promised them a really smooth interface. So missed deadline, I've left it entirely ambiguous as to whether this is an interrupt handler, a software interrupt taskler, real-time thread, maybe regular task. That doesn't really matter too much to me at the moment. We've missed a deadline. When the system gets busy, we haven't said clearly whether it's system testing or a synthetic workload, although the fact it's the QA team that are chasing us might well mean we're full system testing by this point. Also, nobody said the kernel's crashed, so we're going to assume the kernel is fully functional and we've still got access to things like trace and profile buffers. Notes from the kind of fail early school. We're going to assume that we can add code to the widget to detect that we missed the deadline. So usually when a device driver does get service late, it's able to say, oh, I was expecting to be running half a second ago, and print a message. That's all part of the kind of fail early concepts. Having a message issued at the point of failure helps us navigate trace. It's a big deal. It's a very big deal. But apart from the message at the point of failure, print K is not actually that much used for this kind of debugging, because you can't decide where to add the extra log messages. The nature of a widget missing a deadline is usually that it was doing something else instead of meeting its deadline. And the question is, what was it doing? And we don't usually know because we expected it to meet its deadline. So what we're looking for now is mechanisms to discover what it might have been doing instead of meeting our deadline. So we're going to look at some of the tools that we get in the kernel to help us with that. So ftrace, you can use ftrace itself in its regular form, because if you've got a deadline being missed and an ftrace, you can get a fairly good idea of what it was doing just before it failed and decide whether or not it should have been doing that, or whether you've got a mistake in the kind of thread priorities or whatever else. And yeah, even a lightly loaded system will miss deadlines if there are long periods of interrupt lock or the task priorities aren't correct. So ftrace we can use to find out what happened. So like I say, if it's a task running late, we might well simply want to find out what task was running before using regular ftrace or trace points. So in this case, just to introduce some other traces, we've got things like IRQs off and preempt IRQ off, all of which detect long periods of lock. So if we think it's an interrupt lock period that is preventing us from running, we can just do a really quick alternative trace using the IRQs off tracer, and it will tell us which are the longest periods of interrupt lock that we have in the system. I would actually advise people to have a look at this anyway, because it's a really useful number to have, a rule of thumb for how much jitter there will be trying to service an interrupt. You know, I've worked on Linux for a long time. In the early days, that number used to be 10 milliseconds. So we used to have to design systems that were tolerant of interrupt. We actually doubled that for things. We had to design systems that were tolerant of interrupts not firing for 20 odd milliseconds. It's quite difficult. It's better these days, but it's still worth having that kind of rule of thumb number around for your platform and so on and so forth. So we can do the same for tasks, effectively wake up and wake up RT, detect long periods between a task being made runnable and that task actually executing. Wake up RT is limited only to real-time threads, so we can find which real-time threads are coming runnable and taking too long to schedule. The other interesting thing we can play is with static trace points. So I've mentioned trace points. They also go out to yeah, well, it depends how long your audio buffer is. So we've got audio will glitch if IRQs are disabled for more than 2 milliseconds. That depends entirely on your system's architecture and how long you made your audio buffers. Old set-top boxes based on Linux do not have 2 millisecond audio buffers for exactly those kind of reasons. And the tracers will help you find them. And yes, no, it's no longer 10 milliseconds. It's much shorter than that in modern systems. Those are back in the kind of 400 megahertz days and before a lot of the real-time Linux stuff had been upstreamed. That's been a long time that these things have been being upstreamed for. So in the early days, you didn't have a lot of the modern preempt stuff that you have now. So trace points are interesting. Trace points are mechanisms that can trace information to the ftrace buffer based on static code that's in the kernel. And scheduler trace points in particular are very interesting. They are advice from the experts about what the schedule is doing that is interesting. So if you type this command here, the echo shed star into tracing set event, you will get a load of stuff in your trace buffer telling you about thread switching and thread manipulation and things like that. And you will get a that can also be visualized, because now you can do a thread chart from that information. So those kind of tracing systems are very powerful. Like I say, all of ftrace will be covered next week. Well, a lot of ftrace will be covered next week. It's a big tool. We may have missed something, but a lot of ftrace will be covered next week. Perf, additionally, so there is a possibility that maybe it's not simply that we have messed up our priorities and we're doing something lower priority when we should have been doing something more important. We may simply have run out of CPU. We may be doing too much work and we can't fit it all in. At that point, we're going to have to look at performance tuning. Perf is a very powerful profiling tool for performance tuning. That Perf itself is the subject of the final week of this course. It's primarily there to exploit CPU performance counters, but it can also use software mechanisms like high resolution timers, static trace points, dynamic pros. It can gather profile information from all over the kernel. So in this case, I've used a simple flat profile across the entire system. Actually, Perf is system wide. It's saying what is dominating the CPU. Yeah, for anybody who hates pulse audio, you can see this as a pulse audio message at the top. Don't get too excited, because this particular system, I deliberately didn't show the idle time to make the picture better. So what you actually see if you look at a kernel that is idling is you see that it's mostly idle. Just to make this picture a little bit neater, I wanted to show a real thread at the top. So that's what it would look like if there was a thread dominating the system and you hadn't explicitly stopped the idle thread from showing. Again, I can tell you that Perf exists. I can tell you it's powerful. We won't be looking at how to use it for several weeks. So now we're going to start bringing out the big guns. You know, we've perhaps not been able to run ftrace because we didn't have the resources. This is the sort of thing we do when we're struggling. We're now starting to bring out really powerful hardware. So CoreSight is a generic name for kind of all of ARM's debug technology. When we use it here, we are talking particularly about their trace technology, so that when a core is executing, it has this thing called ETM, where every branch, every exception, every return, every memory barrier gets logged. From all that, you can then start to reconstruct which opcodes have executed on the target if you're aware of what's in the instruction RAM. So it's enormously powerful. I say similar power to ftrace. It's not. It's able to see much, much further than ftrace because we get to see every single branch if we want to. CoreSight can go to multiple places. It can go off chip into a expensive piece of hardware that only 3 people in your company know how to use. It can also go to embedded RAM where software can parse it. I'm not going to get philosophical about this one, but we have libraries. CoreSight is integrated into Perf, so you can be using full CoreSight level trace and getting the output via Perf and all the software trace mechanisms. If you crash, you know, if you're chasing those desperate crashes, CoreSight to trace hardware can find what happened, no matter what. But the nature of CoreSight trace hardware is that it's expensive and it does require people to know how to use it, and that information gets lost. Yeah, CoreSight is terrifically powerful. It is a good thing to bring out at this point. If we are studying certain events, we want to recognize patterns, we might reach for BPF. BPF is the other kind of thing we're going to be talking about in this course. BPF is fairly exotic. It is a mechanism to attach programs to hooks within the kernel. And the key point about those programs is they are verified to make them safe to run. It is quite difficult to damage or harm the kernel by adding an eBPF program to it. So eBPF program, if we're missing a deadline, we could pick up trace points. We could start to be logging information about what's happening. We could be looking at stack traces. We can study interesting things about the kernel that could have a performance impact. And we can do it without needing quite as many host resources as ftrace might consume. It's a long shot, I have to concede. In this case, we've brought it up because some of the eBPF tooling has eBPF. Not only can you write your own programs, you can pick up programs from other people. And if we think we're missing our deadline because of power reasons, we might want to bring up other people's power study programs. So this is a power study program that we will look at in more detail in 2 weeks' time, where we've tried to summarize which CPUs are voting for what cluster sleep state and how long they stay resident in each of these power management states. We could also do events of CPU state changes. We could look at these kind of things and gather information about the power system and whether we've basically spun up all the CPUs fast enough to meet the load. If we're missing our deadline because we haven't recognized that we're spinning up the CPUs quick enough, then that's the sort of thing that will come up. Okay, so I promised you a short break at this moment. This is annoying because we're 2 minutes past, so I don't know when to tell you to come back. I will probably start talking again in about 8 minutes time, 20 past in most time zones. Anybody who's, no, we won't only be doing this call. So yeah, 20 past, I think, in all time zones. I will recommence kind of the lecture format. I am here to chat, answer questions, go back to bits before actually. So like I say, we're just going to have a breather because I know this is a really fast-paced course, and we also know that from the feedback. So it just gives you a chance to digest and regroup. We did have a pending question about kernel address space sanitizer only working on dynamically allocated memory. There is an MMU in the system, so most forms of rogue pointers get picked up by the MMU. So you can pick these things up with the address space sanitizer, but you wouldn't. So the main thing we're protecting is, in fact, I'm going to, while I've got it up, I'll bring up the, have I got it? Yeah, the direct map kernel area. So when the kernel comes up, it will use big pages to map all the RAM in the system so that the kernel can address it directly. That's why it's called the directly mapped kernel memory. So that basically means system RAM, assuming you've got less than 128 terabytes, is all directly mapped in the kernel using huge pages. And the reason for that, by and large, is performance. By using huge pages, we don't get much TLB pressure when we reach to these bits of memory. So what it's probably best to think about is kernel address space sanitizer is mostly there to help us with the direct map kernel memory, because that's the one that's mapped in big pages. We might be running past the end here and there. It's double mapped, so RAM will be in there and in the vmalloc area. So you definitely don't want to be reading direct map kernel memory via the 2 pointers simultaneously. That's very, very bad. So it is essentially dynamic memory allocation that we're protecting. It is dynamic pointers into direct map kernel memory. We will pick up other types of problem, but the thing that we're really looking to protect with both the address space sanitizer and the hardware variant is access to that direct map kernel memory, because that's what can basically scribble across the entire system. It also helps us with, I mean, it's not that it won't help us with virtual addresses, at least I don't think it will. So I'm jumping ahead there, we go. Yeah. So I hope that's picked up that particular question. And like I say, if there's anything else pending, then put it in the chat, either to the people on YouTube, it gets copied across, so there's a slight delay in me seeing it, which Christine's doing for me. But yeah, anything else that's coming up, please put it in the chat. And if you don't ask me things, I'm going to have a quick glance ahead in the slides to make sure I can finish on time. couple more minutes, then we can start up again. This is where I prefer using the conferencing tools where people chat at this point, because I feel a bit odd speaking into space while we wait for things to restart. But I have to say, there are so many people booked into this session, we had to run it with microphones off by default because there are a lot of people here. Okay, so I think we're going to wake back up at this point. So we're now looking at the story that I think a lot of people will be most interested in the kind of embedded community. My board just stopped dead. It was running fine, and then it stopped. There's no console messages. It won't talk to me. I can't find a way to get the debug messages from my dmessage buffer. So we'll say that obviously the number of ways and mechanisms that could have caused this to happen is quite wide. It is a very widely scoped story. And we haven't got any clues because the machine won't talk to us. We do not know what has happened. For now, we're going to assume that the hardware is not faulty. So that doesn't mean that we haven't had a hardware-related crash. The bus might have locked up, but if it did, it was because of software stimulation, like reading to the wrong address. It's not the case that it simply burns out the power every now and then and resets. We will talk about that a little bit as we move on, but we're keeping that one out of scope for now. The system and the problem is repeatable and has a software-y sort of feel to it. Obviously, the details in this story are very, very device specific. The board state, including kind of bus health, whether the bus is locked up, whether the power is there to the peripheral you're trying to talk to is unknown. And so at this point, we will have to start. One of the reasons I make sure people understand how debug tools work under the cover is that they are software tools. And if they don't work, that does at least allow us to reason about how badly damaged or injured the board has become. So initial analysis, two aspects to it. Firstly, let's bring back failing early. Everything we talked about in failing early starts to apply here. And the reason for that is that our theory is that, and it's usually true, is the console is still functional if there was any code running that was causing print K. That's not always true. You can break the console, as I said, but it's a good theory to start with, is that it's not talking to us because there is nothing executing on the target that calls print K. So how do we try and find out or make some code on the console, make some code execute that would call print K? So first up, always set up things like early con and init call debug if there are problems happening at boot. Remembering, of course, that init call debug prints at log level 8. So you have to add the log level 8 as well as the init call debug onto your kernel command line. This second line is slightly wrong because init call debug won't identify clock disable unused. But if you see messages about the clocks being disabled just before the crash, you should always turn on clock ignore unused. So the way the clock framework works in the kernel is all the clocks come from the bootloader. We then run through the initialization allowing drivers to come up and probe and grab clocks. And then after the drivers have all been set up, we go through and we turn off any clock that is not being used, including the DDR if somebody forgot to take the clock. So a correctly written system with the correct set of drivers in it should not be turning off critical clocks, and the device tree should be marking up things like the clock for the DDR anyway. But if you see things start to fail when the clocks go away, first thing to do is to see if it survives with clock ignore unused, then start studying what clocks haven't been taken during boot and find out if they're system critical. You should always enable some of the cheaper of sets of the early analysis tools to find out if it's stopping dead because of a deadlock. So debug mutex, lockup detector is worth turning on. You could even look at backporting debug spin lock again. So debug spin lock is a thing that used to be in this presentation and was removed from the early section because it was removed from the kernel. And the reason it was removed from the kernel is that basically it instrumented spin locks so that if they take more than 20 seconds, or 20 seconds, I think, they would print a message to say, I can't acquire the spin lock. And on massively concurrent 500 core newer machines, waiting 20 seconds to spin lock does happen, and it's not a bug. So it was ripped out because they couldn't find a tuning value to stop it triggering spuriously, I believe. And because things like the hard lockup detector cover the same space for PC systems. So if you're in a system where you can't use the hard lockup detector, it might well be worth finding the code finding the patch that removed debug spin lock and reverting it. The other thing I quite often do when presented with a machine that won't talk to me is add a rate limited print to the GIC driver. What that is for is that if a machine starts to fail and it is stuck executing and re-executing an interrupt handler that it can't make stop, in other words, a interrupt handler that spuriously says it's handled an interrupt when it hasn't, it's quite nice to pick those out. So I tend to work with the rate limiting means that we don't harm the system too much. We can usually survive a print every 200, every 5 seconds from the interrupt system. Usually, not always, but it's a good way to find out if we are just hammering away at an interrupt that we didn't mean to. I will state the obvious, and I have had to say this to people before, people who've simply forgotten about the JTAG debugger, that the JTAG debugger is the very, very best tool to investigate a system that's failed like this. The other thing about a JTAG debugger is the very, very best person to tell you how to use the JTAG debugger is the vendor, rather than me. So there are some open source JTAG debug tools. We've got OpenOCD, which Lenaro put a lot of work into getting ready for ARM64, among others, I should add. So we have ARM64 support in OpenOCD. We have things like GDB scripts, which are mechanisms to help GDB study kernel data structures. So you can use open source tools, but you may also have proprietary tools. You may even have tools from your own company that help you do this kind of thing. But if you have a JTAG debugger, don't leave it in a cupboard. The debugger even a JTAG debugger may be delicate after certain types of failures. If you've got a bus hang, then the bus initiator of the CPU is stuck. And if you do anything in the debugger to ask it to read from memory, the debugger will hang up as well because it gets stuck in the same stuck bus initiator. So you have to be careful, especially if the problem doesn't reproduce very often, because it might take several days before you have another shot at it. So the way you like to think about it is you think about gathering state in the order most reliable to least reliable, not the order you want to study it later. So for example, you should always look at the CPU register states before looking at device drivers or RAM or anything else. Maybe from your previous state, you'll then have an idea about which bits of bus you can't act. When a modern bus locks up, it's a tree. So some bits may still be accessible and other bits may be stuck. It's not an all or nothing kind of situation on a modern CPU. So which bits of the memory is safe to look at next is difficult. So like I say, you always gather the CPU register state. Your goal after that is to extract the dmessage buffer and the ftrace buffer if you've got them running. It's especially useful in some systems to learn how to connect without resetting the target. For example, if you've got a bank of 20 devices all running tests and one of them fails after 2 weeks, your customer still hates you for it, but you've got to debug it, and it's difficult to hook up the JTAG debugger to all of them simultaneously. So you then come up and plug it into the one device that's failed and leave the other 19 running. So it's definitely worth knowing how to hot connect with your JTAG debugger, but it's the vendor that can help you do that, I'm afraid, rather than me. So a quick aside about, in fact, this rest of this section is mostly an aside now. SOC level debug. So everything we're going to be talking about today in the Linux side is a software-based tool, and bus hang stops software from running. So it's definitely worth understanding a little bit about SOC level debug techniques. So there's kind of three things to think about that I want to draw people's attention to. The first is the value of having non-CPU bus initiators. They can help with reasoning. Simple things like if you can see an image on the LCD panel and you know that that LCD panel refreshes from the DDR a particular period and will go black if the DDR stops running, then you can use that to prove that the DDR clock is still running because we've got an image on our LCD panel. That tells us that JTAG to RAM is probably better than JTAG to registers. By way of example, if you know the DDR is running, hopefully we can get access to it. Any SOC that has built-in coprocessors or controllers may be able to use those coprocessors to gather information from anything that's memory mapped. If you're lucky, you could get generic peek and poke over a serial port. It does depend on the device. Obviously, a phone, that's rather more difficult. But you can use these coprocessors for quite low-level accesses. And Linux will return the favor. I mean, anytime you have a coprocessor driver, you should have a range for Linux to be able to core dump it if it crashes, so that you can go back to your firmware team and say, look, it's crashed, fix it for me. So anytime you spend allowing you to get core dumps from coprocessors makes it so much easier for you to shout at your firmware teams. Post-reset memory recovery, I've mentioned it already briefly. So with a little hacking, trace tools can be made to target on-chip SRAM. That does mean reach into ftrace and force it to use a weird buffer. It's going in and hacking. But the advantage of using on-chip SRAM is it's fast. And you might get away with running the caches turned off. Memory contents will usually survive a reset, providing the bootloader can bring the DDR controller up quickly enough, and they usually can. However, the caches frustrate the recovery of memory post-reset, because although the DDR survives, the contents of the cache does not. So exactly what you can do to solve that does vary from time to time, but caches are awkward in this regard. And then finally, bus debug registers. Modern SOCs often have secret registers to help understand and debug bus hangs. And like I say, they are usually secret. A lot of vendors don't like discussing them, telling them, because they can be used for all sorts of crazy performance tuning, and they can make the chip break trivially, and so on and so forth. So it is always worth sidling up to your hardware team and finding out if they've got any undocumented bus hang analysis mechanisms. So moving away from that side now, ftrace, if you turned it on, would be telling us which function had just been jumped to before we failed. It's a big deal. That would tell us where we could start adding printfs, for example. As I said, post-mortem trace tools hate caches. The modern caches are very large. They'll be destroyed by a reset. If you're really lucky and you've got other bus initiators on the system that are cache coherent, you can use that to read through the caches and discover what's in the trace contents. JTAG debuggers are almost always cache coherent because they use the CPU's own bus initiator. Or we can try storing the trace where we can look at it later. So RAMOOPS is an example of a mechanism to do this. It's a general framework to store stuff in persistent RAM. It has a non-cacheable mapping by default, I believe. So the contents will automatically be stored. You can target your dump console messages, oops, function tracing there. I will say that if you are doing function tracing with a wide net, the performance costs can be monumental when you're trying to write to uncache memory. So we had an example that we gathered to confirm that. We pointed ftrace at a RAMOOPS buffer, we ran hackbench, and you're talking about a 200x cost in performance for doing full wide trace. Now, bear in mind that you can reduce the cost of ftrace by reducing what you trace. You can try and focus in a bit more on what you're trying to learn about. So you can use ftrace, you can point it to uncache buffer, but you need to be very careful about which functions you decide to run the tracing on. For example, you would probably use a trace point based trace to track the context switches only. And then that would give you some clue of what might have been being executed on the threads, because you know what the thread is supposed to do. And from that thread, you might then be able to zone in. It's that kind of thing. You wouldn't do a full wide F trace. You'd run quite carefully tuned trace points to find the PIDs and all the other things that are happening, where things go wrong, and then you zone in with that information. Anyhow, if you have the information post-mortem, it's very, very easy. You can simply mount the pstore file system and grab the information that's been stored there. Since we're talking about oopses anyway, we'll have a quick message about how to read an oops. Now, this is outside the scope of my board stop dead because we didn't get an oops trace. But maybe the console was damaged, maybe it went to the RAM oops place instead, maybe it's a phone that didn't have a console, so when it stops dead, we don't have a console, and we can go and find the oops by some means. So I'm going to have to go relatively quickly, which is a shame because I know a lot of people would like to cover this. So obviously the first thing we see in an oops is what's actually happened. In this case, it's a fault. We've been unable to dereference a null pointer. There is some other information here, exception classes and stuff you can look up in the user manual, but in the ARM architecture manual, but that's not often that important. It can occasionally be interesting to look at the user page table here. Knowing what size pages and what size virtual addresses you've got, how many steps there are in the page table, tells you the memory map. I mentioned you need to know the memory map. I at the time glossed over the fact that there are, I think, 6 different memory maps an ARM64 system can have, depending on which way it's been configured with the size of pages and the size of VAs. So it's not just a matter of knowing a memory map if you're on a system that, if you're on an alien system anyway, if you're like me and you come to lots of different systems and have problems, then you use that to find out what memory map the kernel will have. From there, you can then go and start looking things up. It's worth having a look at the tainted. So this one says not tainted. Everybody remembers tainted as the thing that says you try to load a non-GPL module, but tainting does much more than that. Tainting lets you know that certain things have happened in the past, like, for example, a soft look has previously been detected. So maybe we're looking at second order effects. We've had memory faults can cause tainting. So yeah, it's worth looking at tainted. If it has a flag set, go and find out what the flag was. And after that, you've then got the registers on the system and the stack trace. So the program counter is obvious, we know what to do with that one. But if the program counter is bad, always look at the link register, because it's very likely if the program counter is bad, we've just followed a bad function pointer. And the place that we just followed the bad function pointer from will be stored in the link register. So those two are always worth looking at. They will all actually, the link register, I think, in modern systems will also get copied into the core stack anyway. When we have VM Linux, the original ELF image, we can load it up into things like GDB and list the addresses to find out what bits of source code they match to. We can disassemble it. We can find out what the various opcodes are going to mean. Is this what we're going to cover? Yeah, okay. So, and the last thing I want to mention is the procedure call standard. This will come up multiple times over coming weeks, so you don't have to remember it all now. But knowing just a little bit about the procedure call standard does make life much, much easier. So the things we've looked at already, the link register, the stack pointer, it's worth having a look at it and making sure it's a kernel pointer and that it's the right type of kernel pointer if you know which type of kernel pointer it's going to be. There's some stuff in the middle which is interesting to know, but mostly only because that's where the compiler will start to prefer certain registers, like during function preambles, it'll hit R19 a lot quite commonly. That's because of some of these properties, but until you get quite into the reading disassembly, it doesn't really matter. The one that really does matter to us is these parameter and result registers. If you are stopped at the entrance to a function, then R0 almost always is the first argument to the function. R1 is almost always the second argument to the function, and so on. That's part of the ABI standard. It passes the first 8 parameters in registers. So unless you're writing insane code with 20 arguments, then at the point you are stopped at the entrance to a program, we can see what its arguments were. And with a little bit of care with disassembly, which I think we'll look at in the next episodes, you can actually look through the function preamble and find out where it stored the variables and it's worth knowing a little bit of disassembler, not much, and we'll cover it coming weeks in fragments. But in this particular case, we're looking at a oops trace. We can see it's in sysrec handle crash, which is the sort of thing a trainer does to make it crash if they need to get an example. X929 is a pointer to the stack. This is good. That's what we expect. You can see this particular one has not got a VMAP stack, I don't think. Yes, it has. That is a VMAP stack one. X8 is not a pointer. Sometimes it's worth checking that. If you are doing big structure returns of the copy rather than by reference, then you'd see that in X8, it will be a pointer to this big structure, but that's to do with the function prototype. And then finally, we've got X0, X1, X2, X3. They could be arguments, but let's check the C because we're not actually running at the entry point anymore. So we look at the C and we see, it's not actually using the argument, so it might well get splattered. And in actual fact, if we go back through and study the disassembler over time, we would see that. The major one here actually is you can see the movement to W0. This is the one that tells us it's been overwritten because we've copied 1 into it unconditionally. Move moves the argument into the register, and on ARM64 systems, X means access the register 64 bits wide, W means access it 32 bits wide, and it's the same register. So this will cause R0 to be clobbered. And we could then study some of the other bits to see where things have gone wrong and so on. But a lot of this stuff we'll come back to and we'll visit over time. I encourage you to have a quick read of these slides. You've got the links to it, but I haven't got the time to dive deeply into that particular subject. But essentially, don't be afraid of hardware level. That simple knowledge, if you're at the entrance to a function, R0 through R7, R function arguments, gets you a very long way. If you can also learn to read loads and stores and moves and no other opcodes at all, so if you can learn 3 opcodes, it's amazing what you can do with that bit of information. Okay, so other things we could be doing. So core site comes back for 2 reasons. Firstly, we've got trace. So I mentioned that really powerful trace. Now, if the JTAG debugger is broken and we can't discover anything from it because of various bits of bus lockup, if we attached to a trace port and traced each CPU jumping to each piece of code into a off-chip piece of hardware, we would know what opcodes it was trying to run at the point it failed. Period. We would know. There's no 2 ways about it. There's no real ways that it can fail. The problem, of course, as I mentioned, is that trace hardware is expensive, difficult to find, and most people in the company don't know how it works, even when they've got it in a cupboard. We had one of these in a company I worked for, and it did literally live in the cupboard. It was very, very expensive at the time. It was a 5-figure sum to buy this thing, and there were like 2 engineers who knew how to use it. It's not an uncommon pattern. It's worth going to find the engineer that knows how to use it and talking to them. However, there are some cheaty ways we can do to exploit core site, and that is based on the knowledge that the last program counter that we had a trace event for, which means the last branch we took and things like that, is stored in the register state of each of the trace units. It doesn't necessarily, it can be written out of memory. It is also stored in the register state. So if we can get to that register state without resetting, then we can find out just the last PC. And that's huge. It's not as nice as having the full trace, but it's huge. Because knowing the last PC gives us the chance to attach trace, to find out if it's constant, if it's always the same address, and so on and so forth. So it's in the register set. You can, if you're lucky, use a non-CPU bus initiator to suck it out. So if the whole system's dead, but you've still got your front panel microcontroller working, you might be able to go in through that and reach onto the ETMs and drag out this value. There is also a multi-CPU watchdog kind of thing that was implemented. It's called Core Site CPU Debug. If only one CPU is dead, then other CPUs can reach in and extract it. So it's not as effective as a lockup detector, but if you've got something like an RCU failure coming up, you could reach in and ask one Linux SMP partner to watch the other. Effectively ask it to find out what program counter the dead core has been running. Okay, so lurching in a wholly new directory at this point. I'm sure this used to work. This is very common, amazingly. I ran this test a couple of weeks ago, and I then haven't run it for a bit because I haven't got CI loop, and it used to work and now it doesn't. This is probably the narrowest story we have, although we don't know how complex the test is. The reporter is probably a bit ad hoc. We're going to assume that such a reporter has not been very rigorous about their configuration management. So first observations, the kernel source code is very strongly version controlled using Git. And hopefully most developers are in the habit of checking in frequently enough that they can also use Git to try and spot changes in the code. But there are other parameters that quite often are not as well controlled. So the kernel config itself, I mean, it's quite common for bugs to come and go as the kernel config changes. And it's another dimension that you can move through. The other thing is that most people forget that they upgraded the compiler. So if you've gone from GCC 8 to GCC 9 and then 2 weeks later you see a bug the first time you plug in a platform, you forget that the compiler's changed. It really is very, very easy to forget that. So if you're sort of staring at something that used to work and you think you've controlled everything, then look for those things you didn't. It can often be the compiler. It can also be the user space for kernel developers. Some kernel developers pay so little attention to user space, they just completely forgot they changed it. That's rarer. But there are kernel developers that kind of forget that sort of thing. So first up, you have git bisect. This is used to try and study two different kernel systems, one that works, one that doesn't work, and to try and find the commit that made it break. So essentially, it's regression hunting through the version control system. So there are multiple ways to run it, but I am going to particularly illustrate git bisect run. And that then runs a shell script that will actually do the test for us. It has a number of return values. It compiled and the test is okay. It compiled and the test failed. It wouldn't compile, so we were unable to run the test. Please go and find me something similar. So these do map to the good, bad, and skip options to git bisect very directly. And it may feel like it's difficult to write compile, kernel, and test because it may need you to use a manual step like trigger a PIA cycle or type something into the bootloader or everything else. Firstly, I mean, software control relays are really awesome. They do make searching through empirical searches like this much more pleasant. But even if you have to have some manual step, I would still write a shell script to tell you what to do. There's a couple of reasons. Ultimately, it's errors. If you type the wrong thing, git bisect, git bad, git skip ends up in your bash log history, and you press up and down, and you accidentally click the wrong thing, and then you keep going for another 30 minutes, and at the end of 30 minutes, it tells you the bisect was mismatched. And now you don't know whether you made a mistake or whether the mismatch is because the bug does actually come and go. It's not 100% reliable. But you don't know when you run it again for 2 hours. So I assert that there's so much probability if you're doing git bad, git skip, git good with the command buffer that you should write a script that tells you what to do. And then probably make sure that the script also rings the bell in the terminal and do something else. And every so often you turn to the bell, you go and find out what happened, you do whatever manual step is necessary, and you go back to something else, even if it's watching a YouTube video, preferably a training YouTube video rather than something that get you fired. But yeah, even if you're just occupying your brain while waiting for something to happen, providing it's moderately constructive what you're doing, it is better to get the computer to tell you to go and check things and ask you to check and look after yourself, because it's really frustrating to get to the end of a 2-hour bisect and be told it's inconsistent and not be 100% sure you implemented it correctly. Other thing I'll bring up is ktest.pal. So it's a Perl script. It's found in the kernel sources. It is very heavily commented, although it's undocumented. And it can be used to automatically run tests on targets that do have a remote reboot. This one doesn't have a shell script really. You do need to have some remote capacity to reboot this device. So you can simply use it as a high-level framework for running bisect to replace your kernel compiler test, but it has support for other types of empirical testing. In particular, you can hand it a good config file and a bad config file and ask it to tell you which bit of the config file makes the good one good, or the bad one bad, if you prefer. That's a really, I mean, it's not perfect because sometimes it gives you 30 config options, but it's a much better than the sort of 200-300 different config options that you quite often get in a first diff. So where you have that capacity to remote reboot, then bisecting a config file is a really nice way to go. Just some trivia, in case anybody wonders. ktest.perl is the same gentleman, Stephen Rosett, who we have to thank for ftrace. And then finally, I will warn you before I put this up, this one is slightly anticlimactic. So the story is my board just randomly failed. I wasn't doing anything really special. My board just failed for no reason. Maybe it was having a workload, it was a bit busy, but it has just stopped. I mean, this is as wide a scope as you possibly can. It is just a random failure. A couple of bits of philosophy though. It is not a compiler bug until you can show a bad opcode and say why the compiler was not permitted to emit it. Compilers are really complex pieces of software. The optimizers do amazing things to your code. Most of it good, but optimizers do amazing things to your code until you can step through and show the opcode. Then compiler guys will struggle to take you seriously because people tell them that compilers are broken all day long, and most people that tell them the compiler is broken are wrong. Simply, so yeah, you have to be able to find what has happened in the compiler, why, and that's when you can start blaming the compiler. Almost the same with a hardware bug. It's not a hardware bug until you can show what the hardware's done wrong. However, because hardware is slightly more vague and has interesting electrical faults alongside everything else, you can make do with simply powerful evidence. You know, you think about it that you have to have a sufficiently strong evidential trail that your manager can look a hardware manager in the eye and say, we need your help. That's ultimately where you're heading for with hardware bugs. So there's lots of problems to be done here. At this point, we're starting actually to move away from kernel debug, which is the subject we're all here to talk about. What I mean by that is that kernel engineers are often exposed to weakly validated hardware, especially for commodity interfaces. The validation team don't really know much about USB. They very rarely know anything about PCI in many companies. Wi-Fi, again, it's a specialist subject, and it's usually coming down to Wi-Fi, less so for kernel engineers because there's usually a Wi-Fi specialist on the team. But things like USB and PCIe, when they are broken, it's complicated. The validation team might not understand what's going on. They might even be the one to find it. It's often the kernel engineer that finds these things. It's not because the validation team are doing anything wrong. It's the nature of complex commodity interfaces. The specialists in those things should not be in your validation team. Why waste their expertise there? Validation experts should be in a validation team. So the other thing to bring up is the effect of SMP race conditions and memory corruption are ultimately non-trivial to distinguish from one another, because the nature of an SMP race is that memory changes value in an unpredictable way, or at least in a conflicting way between cores. And there aren't that many tricks. When you're at this level of random failure, ultimately there is going to be hard work involved. And that hard work can be done ahead of time to make things a bit more comfortable. And there are things we should be doing when the problems have started to manifest themselves. So, I mean, first off, kernel drivers or the bootloader should find every possible reset reason you can possibly find and print it. Especially so if security hardware in many systems has a nasty habit of rebooting if it's unhappy, and it tries to not tell you that it's done so. So finding ways to, even if you don't make it too conspicuous, recognize that the security hardware has become unhappy and resetters is worth knowing. More so perhaps in set-top box than anywhere else, but as security is traveling through the world, it's becoming more and more common that those really hardcore security attitudes of if somebody's tampering, reset immediately come up. So obviously anything that's manipulating voltage, power supply changes in particular, needs to be traceable and disableable. Like the hardware bugs, Just the fact that turning off power supply changes makes the problem go away does not mean it's not your job to fix it. It's simply evidence, but being able to gather that evidence is quite useful. Having a P-store driver so that you can try and get some information back after reset is useful. The best thing to do with an SMP bug is not to write it. And that means that's not, it's written in a facetious way there, but it means don't be clever. You know, if you use classic spin lock, spin unlock, then the barriers will be correct if you've got everything matched up, and every time you touch the shared data, you are working through a fairly direct, simple lock-based algorithm, then you are much less likely to write SMP bugs. If you do complicated lockless things without locking and sharing data to pass messages and things like that, you'll have SMP bugs. You know, the very few people in the world can write that kind of code without making a mistake. Not the first time. I mean, some people are then able to debug it after the fact and find the problems, but yeah, don't assume you know everything about SMP. Try to stick to the simple patterns unless there's a really strong performance reason to break out of it, and automate everything. There are some things to do when problems occur. Most of this is to do with having that summary of investigation. I mentioned that you might have to have a conversation with a hardware guy, and you have to be able to tell them what you've done, and you have to be able to demonstrate that you're credible and what you're saying is sane, and that there is a reasonable chance that there is the hardware at fault. So obviously you don't start summary of investigation on the first day, but certainly if ever you're debugging things where you're going to your manager and saying, yeah, this could take weeks, I can't tell you, maybe I'll solve it tomorrow, maybe I'll solve it in 10 weeks time. I don't know. When you're saying those kind of things, and it's quite reasonable when you're facing a challenging bug to have no idea how long it's going to take, and you've not got much traction on it, it's hard to find out what's going on. That's when having that summary of investigation, knowing what you've tested, what theories are, being able to tick off the ones that are disproved as you go. So if you're handing over to hardware people, you can say, we know it's not this because we saw this, etc., etc. That kind of thing. That strong, clear, almost scientific log of what you've done is useful for reasoning, and it's also useful because if you have a good quality summary and somewhere someone says, has it done this? There's somebody in a coffee shop, coffee room, you're just chatting, and they say, did it do this? And you say, I don't know, but I'll have a look. And you look through your historic logs and your historic traces and memory dumps and the records of the things you've tried, and you should be able to say, yes, it does, or no, it doesn't, or we can't tell, but we can design some more experiments. But in particular, if the information's there, you can take new theories and disprove them quickly if they're speculative. But that's ultimately one of the things that we could do with those kind of logs. You should always, 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 on any random failure, get another board and another power supply and check it works again. And even if it doesn't feel quite exactly the same, third board, fourth board, fifth board. Because ultimately, if you've got some kind of manufacturing marginality, then that's already a strong evidence of non-software involvement. When things are happening at completely different times in the boot on different boards, that can become quite quickly evidence that it's not really a software style thing. It's not sufficient on its own, but you should always, always replicate on a different board. If your board's faulty, throw it away, get a new board. All the usual failure techniques still apply, but we might want to introduce things like always on memory testing. So memtest, config memtest, it's an uppercase thing there, does do a boot time memory test, but it's basically just an addressing test. It's not very helpful. And I'm not a great fan of just launching those look for bit error tests on a single core and leaving them there, because there are so many bus interaction problems that they don't find. So bit error tests are really quite useful, but I like to see them always on. If you've got the capacity to run some kind of always on memory test somewhere, either in user space, hitting as much mapped memory as you can, or maybe even a coprocessor, it's a good thing. You don't have to test all the memory all the time, because if you've got bus interaction errors, they manifest across the bus. So it's actually to do with simultaneous bus transactions that you're trying to cause to get these kind of random problems to occur. So it's the memory test that will eventually hit the problem in the timing on the memory interface. It doesn't actually matter. For example, one of the common things here is the DDR timings aren't 100% correct. So that always on memory test will eventually hit a bad cycle on the DDR, regardless of which addresses you're targeting, usually. So yeah, when you've got really strong random problems, those kind of always on memory tests are worthwhile. I haven't got time for a war story, but I do know from personal experience that one. Core dumps, again, can be quite useful if you're able to gather them, because if you have managed to get one, particularly dumps that show oops traces and kind of like impossible situations, that's a really good way to prove that things were fetched incorrectly. If you've got a bad fetch from RAM or a bad iFetch, then if you can see impossible manipulations of the registers based on a scan of the disassembly, that's really powerful. That's quite low level, but it's definitely worth being able to do. And the final thing from me is a quick aside about memory barriers. So this is all part of not being clever with SMP, because a lot of people don't think about memory mapped IO when they start thinking about SMP race conditions. They start thinking about ordering and who sees what when, and somehow the act of reading and writing to registers gets neglected in all this. So first off, with the default accessors, which have barriers inserted into them, they're almost always safe. You know, when you do things like read all and write all, then the order that you see in your program should be both the order it happens on the hardware and the order that other people observe it to happen. Modern codes also have things like the relaxed accessors, read all relaxed, write all relaxed being the most common. And it's not uncommon during reviews to somebody say, well, read all write all is really slow. Try read all write relaxed, it's much faster. Nobody who knows what they're talking about should ever advise you do that on a driver that's using DMA, except possibly in small areas where you're setting up kind of descriptors that haven't hit the trigger button yet. It does depend on the DMA addresses and things like that. But yes, understanding that you have these accessors that have memory barriers, you have accessors that don't have memory barriers, and that ordering in certain ways is not guaranteed, particularly across observation of results. A single CPU doing reads and writes will see the correct ordering, but that's the CPU observing it, not the order it actually happens in. Will Deacon has an excellent talk about I/O and effective memory barriers. That was done at ELCE 2018, I think. So if you're interested in the really fine detail of it, you can dig out the YouTube video of that. And at that point, we run to the end. So the free gift is hardly as exciting as you might like it to be. But just occasionally, when you've told your manager that you don't know where you're going and it could take you any length of time, and what you're really saying is, I haven't got a clue what's going on, I don't know what to do next, knowing the tools is going to give you a better chance. So this poster here is essentially pretty much, I think, every concept that we've discussed today in a single image, and the size is related to how frequently we've talked about them. So roughly speaking, the importance of the different concepts. Perf is slightly oversized because I think we put a slide up where we said perf, 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 and so perf ends up slightly bigger than it should be in this particular image. But it's a collection of interesting ideas. You can just stare at it and see if there's something you haven't thought of. I know a very small number of people have printed this out compared to the number of people I've trained, but we put it up anyway just in case. So yeah, if you're interested, it's there for you to take. I will say that for everybody who has attended this session, we have the lifetime warranty, which translates, roughly speaking, to anybody who receives this training from Linaro can ask questions about it now or at any point in the future. This doesn't mean I can give in-depth consulting on advanced kernel debugging for free necessarily, but if you can put a slide number to the question, I can answer it. And in actual fact, for members, and this is actually a member presentation, so for members, then we can do much more for you anyway. You can ask questions about anything related to Linaro, whether it's our training material, the work of the kind of working group, the power management team, anything that Linaro works on, you can ask at support@linaro.org, and it's our job to dig out an appropriate answer for you. So, you know, support@linaro.org doesn't just go to me, but I am the tech lead for the team that runs it. So I will see anything that comes through. So anything that's come up today in training and you wanted to ask about, yeah, please feel free to use that. Likewise, if you decide to do the lab exercises and you have any problems, that also is where you should go. So the final thing is to mention the lab exercises. Now, the lab exercises are entirely optional. I don't have any means to find out if anybody did them or didn't do them. So we've covered a lot of different tools today, and the lab for this week is fairly small, to be honest. And the reason for that is we are focusing on tools that we can A, work on a simulator so that I can give everybody the same exercise, and B, that we're not going to come back to in a few weeks' time. So this means we can't be doing advanced core site stuff because the simulators don't include any core site. And additionally, core site is implemented differently on every single SOC. So there's no way I could offer such a large body of people exercises on core site anyway. But we have got a few small exercises for some of the earlier stuff we talked about. You can also look at the failure list stuff, which I don't think is covered very much in this section. So the way this is set up is we've offered a have I got the wrong slide there? I think that slide shouldn't be there. That's what's going on. So let me remove that for you so it doesn't confuse anybody. I beg your pardon, I think that's from a different course. So Lab 0 is just a recompile to start you on the kernel. It takes quite a long time, but you'll be able to use a binary kernel for the first exercise anyway. So you can set it running, building, and then move on to Lab 2 if you want to keep going. Like I say, this session, have a quick look at seeing what we're working with. It's stuff you're familiar with. There's absolutely no need to do the lab exercises. I will push quite hard the lab exercises next week. So of the whole course, I think ftrace is the tool that you come to most frequently and that many kernel developers can stand to know a little bit more about. So I'll push the exercises really hard next week. But for this week, look to see if you think you'll get something out of it. It does depend on your level of experience whether it's going to be right for you. And that's us at the end. Now, there were a couple of comments as we went through. I don't know any questions. So there was some comments about using decode stacktrace.sh, which is in the scripts directory in the Linux kernel, which can automate the conversion of function plus hex number into symbol lines for you. Yeah, that's a really good point. We should add that in here. So this doesn't let you look at things like the variables. You'll still have to fire up your editor, but it means you don't have to use the debugger to study these things. And somebody's added something that's Android specific, and I haven't picked up on before. So I don't know what that link actually goes to, but somebody shared a link to the Android website where there's a section on debug. There is actually some very good stuff on ftrace that we will bring up from the ASP, not ftrace, from perf. There's some really interesting stuff on perf that we'll bring up about Android in the last week that I picked up from exactly this site. But yes, I'm happy to lurk around for a few more minutes if there are any questions coming in the chat, but ultimately I have nothing more to say. So unless people say things to me, does add to a line work for DLKM modules? So dynamic loaded kernel modules are quite exciting because you have to find out where they're loaded from. You can't use addr to line directly, I don't think, but you don't use the address necessarily. You can use the offsets, so you can look at the function name plus offset, and that should look up correctly. I usually use, I have to say, I haven't had to look up in modules for a long time. I classically used to use hand-crafted commands in GDB to tell GDB where I'd loaded the module. But yes, if I was doing it looking for the source information, I would look at the offset against the symbol rather than the absolute address, because symbol plus offset still looks up regardless of where you load the module. Was there anything coming on YouTube, Christine, or are we quiet in YouTube land?
Yeah, nothing on YouTube.
Right. Well, I think at that moment, I'm going to say thank you all very much for coming this week. Like I say, next week we will be talking about ftrace, and in particular ftrace without tools to support it. Ftrace is almost unique in that you've got access to immense power using just Linux command line tools. So that's the focus for next week, and I look forward to seeing you all then.